So I see there's still people coming in. So I'll just make some of the announcements we normally make at the beginning instead, to give everybody a chance to settle in, figure out how to use Zoom if they're new to that kind of thing. So we hold these meetings every month. There'll be another talk in November and the final one of the year in December. That'll be our Christmas lecture, by the way. So if you miss these, you can contact the Society and we'll give you the Zoom link. You might notice it's just being recorded there. And that helps all of our members around the country, because we have thousands of them. And we know a lot of people like to hear these monthly talks. A little bit about Astronomy Ireland. We have a magazine called Astronomy Ireland, comes out every month and tells you what to see in the sky. We do lots of other things, these monthly talks. There's lots of events coming up. We'll be getting back to our events now, hopefully when all the restrictions are lifted on October 22nd. Looks good at the moment, but there'll be an official announcement by the powers that be about that. And then the big event, our Starbecue, our barbecue under the stars, will take place, we hope, on October the 30th. Everything's certainly set for that date. We're just waiting the final confirmation because there are rules and regulations of the venue that we use, which is owned by the GAA. So if you've got your tickets, I've been very, very certain it's going to go ahead on that date. We had to postpone it from last year during all the lockdowns. And we certainly don't want to have to wait till next year's one, which, by the way, is already set for August 27th, 2022, if you want to mark that on your calendar. The other thing that's going to be happening between now and our November meeting is that our evening classes are taking place. They run on Tuesday nights, 7 p.m. to 9 p.m. And full details are on astronomy.ie. If you haven't signed up for those, go to the website after the lecture or the next few days and get signed up as quick as you possibly can. I see people are still being admitted. So normally at the end, I tell people what to see in the sky. It's all in your magazine. If you don't get the magazine, you can get that through the website. But I'll just tell you very briefly about some of the highlights, because we do normally send out an email to all members on Wednesday morning. But we've been having problems with our website hosting service. We don't seem to be able to send bulk emails yesterday or today. So the big thing in those is that Venus is going to be close to the crescent moon on Saturday evening. Now you'll need to look as soon as the sun sets in very bright twilight. I've found where to find Venus from my location. You should try it over the next few nights so you're not rushing around in just the few minutes that you have between sunset and an hour later, Venus itself will set. So find out where that is on your horizon, or if you need to go somewhere where you haven't got trees or buildings in that direction, and find Venus, because at sunset on Saturday, it's going to be very close, about 3 moon widths away from Venus, which should be quite spectacular. You'll see both with the naked eye. I can see Venus with the naked eye, once you know where to look, even in very bright twilight. And the moon next to it will just add to the spectacle. And if you've got a pair of binoculars, like the ones that we're going to raffle off here this evening, then at the end of the talk, by the way, so do stay for that, because everyone who's booked a ticket for this event will actually be in the raffle, and someone's going to win those binoculars. So make sure that you check out Venus on Saturday. That's the big thing, because our email list is down. All the details are in your magazine, but it is one of the highlights of the month. And it continues, or the moon continues to put on a great show. Next week, Wednesday and Thursday, you'll actually have the planet Saturn near the moon, not as close as Venus, but in a darker sky. And then even on Friday of next week, the 15th of October, again, all in your magazine, Jupiter gets quite close to the moon. That really is spectacular, because they are the 2 brightest objects in the night sky at that time. So don't miss that. Let's hope for clear skies. The moon itself on Friday, 22nd of October, very important day when those restrictions are lifted, is near the Pleiades star cluster, and that's another highlight of the month. So there's a few things that are coming up. The evening classes as well, don't forget next Tuesday. And I won't say this again at the end, the Starbecue is set for October 30th, and we've already had phenomenal number of bookings. I see there's one more person waiting in to be admitted. I don't think we'll wait for anybody else. That's enough announcements. So we will get on with the show, as they say. So we're delighted to have as our main speaker this month, during World Space Week, which runs all this week, George Tahu, who's now the program executive for the Mars exploration. Well, sorry, I should give him his exact title. He's the program executive in planetary sciences for NASA's Science Mission Directorate. He was a former acting deputy director for the Mars exploration program. He's obviously working on the Perseverance rover mission, which is what he's going to talk about to us this evening. But previously, he's worked on the robotic lunar lander development, an astrobiology CubeSat, and you may have noticed in the news recently were those first pictures from the Bepi Colombo mission to Mercury, and he has worked on that as well. But we've been following very closely in the pages of Astronomy Island magazine all the discoveries from the Perseverance rover, including that fancy little helicopter that they have, which has been providing great fun. It's a superb mission with very important objectives. And we're absolutely delighted that for World Space Week, we could have somebody of George's caliber tell us all about the Perseverance mission. So over to you, George, and thank you very much.
Well, thank you very much for inviting me to talk with your group. And as I said when I joined, this is one of the most enjoyable things for us to do other than launches and landings, just reaching out and sharing our story. So I appreciate you inviting me to come along. So I'm going to share my screen and try to get my presentation up. Are you able to see that?
Yep, that was working great for me.
Good deal. Okay. Anything else arranged here? Oops. Let me go right. All right. Okay. So as this is how we started off last summer, July 20th, 2020. This is a picture of Cape Canaveral, Florida. At the time, it was called U.S. Air Force Station, Cape Canaveral. Now it's called Space Force Station. And there's our Atlas V launch vehicle headed on its way to Mars. It was a beautiful morning. Got off on the first launch opportunity and got us off to a good start. After many years of hard work, design, development, to get this thing ready to the launch pad through all kinds of trials and tribulations. Oops. So, and you know, this is our destination, right? Mars. Today, this is an image from the Curiosity rover in Gale Crater. And as you can see today, Mars is a very cold, dry desert, not hospitable to life. There is, you know, it's bathed in radiation, and you know, not a place that you'd want to be without a spacesuit or shelter of some sort. And even microbial life probably wouldn't be able to survive on the surface. Hang on, I need to rearrange my windows for a little bit. Oops. Okay. Let's try. So while that's how Mars looks today, from the missions that we've sent over the past several decades, we've gathered enough data and information to get a picture of what Mars might have been like several billion years ago, when it was potentially much more like Earth. About 3.5 billion years ago, that's about the time on Earth when microbial life began to arise. So a big question is, well, if Mars was more like Earth at their early, if they had early similar birth stories and early evolution, if it was warm and wet and had an atmosphere and protected from galactic and solar radiation, could it have also been an abode for life like Earth was? So that's one of the big questions that we have, of course, as we study Mars. So that kind of picture has been built up over the decades of the various missions that we've sent. Now, these are really just the most modern ones that we call the missions since basically 2000, when we kind of reformulated, restarted our robotic Mars exploration program at NASA. And you see here images of the different NASA missions as well as international missions from many different partner space agencies that either NASA might contribute an instrument to those missions, or the other way around, where, like, for instance, Mars Reconnaissance Orbiter has an Italian radar on it. Mars Express and ESA mission has US instrumentation on it. And of course, we're all working together, sharing data, trying to be as collaborative as we can to build up the best picture of what Mars is like. And over time, we've been evolving what we call our science themes. In the earlier missions, we had this theme called Follow the Water, looking for evidence of water, where it might have been, how it might have shaped the landscape. And once we determined that, yes, indeed, there had been long-standing water on the surface, that led us to be able to ask the next question of, well, was that environment, did it potentially be habitable? Did it have the right conditions for life to arise? So that's our theme of exploring habitability. Started with the Curiosity rover and now continuing with Perseverance in some ways. But Perseverance takes it the next step. We can actually seek signs of life directly. It has the right kind of payload to try to seek that answer. And all across all of these missions, we also have a goal of trying to prepare for future human exploration. So on several of these missions, you may have a payload that can address key questions that the engineers that want to design future human exploration systems can inform that design. So on Curiosity, there was a radiation monitor. Also on Mars Odyssey, the early orbiter in 2001, there was a radiation monitor to monitor radiation on the way to Mars on the transit. And the Perseverance rover, we've got a couple of things too that are preparing for humans. Now, the other key thing about Perseverance is we are the first step of what's called the Mars Sample Return Campaign. So this is the beginning of the first round trip to another planet. Think about that, first round trip to another planet. We're here, we've started, it's the first leg. This is where we want to use Perseverance to collect samples in tubes about this size, well, exactly this size. This is a scale size model of the tube. And we carried 43 tubes on board Perseverance that we can fill with rock and regolith. So we'll be able to collect what we have, leave them on the surface, and then the next segment of this campaign is the retrieval. So we're working with the European Space Agency. The next two legs are a complete partnership between NASA and the European Space Agency, so that we can send, the first step is this, both what we call a fetch rover to retrieve and go and pick up these tubes that Perseverance will leave on the surface. And then the fetch rover can bring them back to the lander, which has the what we call the Mars Ascent Vehicle, the small rocket that would be able to, the fetch rover would be able to load these tubes into a small spherical container. We call it the orbiting sample container. That is at the top of the nose cone of that rocket, which can be launched into Martian orbit and release that orbiting container into Mars orbit. Then the third piece is this Earth Return Orbiter, largely contributed by European Space Agency, but then what we call the rendezvous and capture system is the payload that NASA contributes. This orbiter will rendezvous with that sample canister, collect it, bring it inside the orbiter, seal it up, breaking the chain of contact between Mars and Earth for planetary protection purposes, and then use solar electric propulsion to spin out of Martian orbit and come back to Earth. Then it has a small Earth entry vehicle, small just capsule, and that will re-enter Earth's atmosphere and land in the Utah desert. Then we will have the very first samples from another planet here on Earth to study. So what is Perseverance looking for? When we're saying seeking signs of ancient life, we're not looking for fossils, large macrofossils, like you might think about, like these on the left-hand side, Earth fossils. What we're really looking for is these microbial fossils. So the right-hand picture is what are called stromatolites in the Australian outback. And it's these types of layers of microbial mats that build up over time that then become fossilized. So if we found something like that, is the type of thing that we'd like to see on Mars. Because here on Earth, this is about the oldest type of life form that we've found, 3.6 billion years old. Now here on Earth, we have plate tectonics, so it's very hard to find anything this old. These things are extremely rare. Plate tectonics churns the surface of the planet over, and the ancient record is quite clean. But on Mars, not having plate tectonics like that, there's a record of a much older surface. So Perseverance has 4 main objectives. First, in two key parts: it's searching for that ancient microbial life and preparing for future human exploration. In seeking life, first we want to understand the geology of the landing site that we arrived at, so that we can then start doing astrobiology investigations, trying to look for those what we call potential biosignatures. And these are either structures or chemical signatures or mineralogy signatures, and or organic measurements that become pieces of a puzzle that the science team can put together and determine could this whether it's a rock sample or a formation potentially be a sign of ancient life. Then we want to, as I mentioned before, put these tubes in a container. Actually, we'll just leave them on the surface. The next mission will put them in the current container. And the last thing being that preparing for humans. And we're doing all this using a very similar launch system, and entirely, in fact, the same rocket, same type of rocket, the Atlas V rocket, and then the same cruise, landing, and surface type design that Curiosity had. So if you put Perseverance and Curiosity rover next to each other, they almost look like identical twins, but there's definitely a lot, several key differences in terms of the payload that was brought. But other than that, the main cruise and approach and the Skycrane landing system were effectively built around. So here is our rover, and I'm going to talk a little bit about our payload. Start going clockwise, starting in kind of back in the rear. This is one of our contributions from Norway called the RIMFAX. It's the very first time we've had ground penetrating radar on the surface of Mars. Then up at the top of the mast, we have our big eyes, the Mastcam Z. Z is for zoom. This is the next generation version of what was on Curiosity. And then SuperCam, also the next generation. Curiosity had ChemCam. This is SuperCam. And it also has a laser that it can fire at a distance to rock formations. And when the laser hits it and makes a small bit of plasma, the telescope on SuperCam can see that plasma and then get a sense of what's the makeup and composition of the rock from a distance at a bulk level. That can help the science team decide, oh, is that an interesting rock that we want to drive up closer to? And then use the instruments on the end of the robotic arm to interrogate further. So down the mast, we have a variety of sensors spread across. That's a contribution from our partners in Spain. Oh, and I forgot to mention on SuperCam, it's a half collaboration between Los Alamos National Laboratory here in the US and a consortium of French research institutes. So more international partnerships. So Spain's contributed this set of sensor suites to get temperature, pressure, humidity, also a small camera to look at the dust in the atmosphere to study that. And then on the end of the robotic arm, we have the Sherlock and Pixel instruments, Sherlock being an ultraviolet spectrometer, laser spectrometer to look at the mineralogy. And if you have Sherlock, you got to have Watson along with it. And that's the small micro imager, like a hand lens, high resolution camera at the end of the arm. Pixel being an X-ray spectrometer looking at the chemistry of the rocks. And these can, now the other thing in between those two is the heavy rotary percussive drill. And that's where we have at the end of the arm, there's that drill, and it has these, we have several drill bits like this. Okay. And the tubes are inside the drill bits. So when it drills into the rock sample is going directly into the tube. Then we can use the robotic arm and dock to the front of the rover, kind of like right here. You'll see what we call it's the carousel where the sampling system is pointing to. And inside, then it'll rotate this down inside of the rover. There's another smaller robotic arm inside On the left-hand picture, you can see what that system looks like before it was put in the rover. You see that small robotic arm can then pull this tube out and then being able to manipulate it to several stations. First one, we have a camera to look inside, make sure there's something in there or how much. We have a volume probe to get a sense of exactly how much sample we've got. And then we put it to the sealing station where we put a cap in it that hermetically seals this tube. Then we move it over to our storage rack and we'll wait until we're ready to drop it out the bottom of the rover. So the last piece is MOXIE. This is a system that's inside the rover, and this is that key piece of our preparing for human exploration. MOXIE produces oxygen from the Martian atmosphere. 90% of the atmosphere is carbon dioxide, but if you can suck that in, heat it up, flow it over a catalyst, you can split the CO2 into carbon monoxide and oxygen. Then we have sensors that can measure the purity and amount of oxygen that's being developed. And this has been run, we've done several MOXIE runs since we've been on the surface since February, and it has worked extremely well. So this is an example of a technology that when you eventually send humans, you'll need it both for generating oxygen for breathing, but as well as generating the oxidizer for rockets or other fueled systems. You certainly need that to get home. And you'd much rather be able to use the resources that you find on the planet, basically living off the land, instead of bringing the mass of all of that with you from Earth. So here's a short video of some highlights of as we were building and developing the flight system. All of this, most of this was done at Jet Propulsion Laboratory in Pasadena, California. Now we have vendors all across the country, and I mentioned our international partners. We also have vendors around the world, many European vendors particularly. And once we bring all of that together at Jet Propulsion Lab, then we have to do the assembly, test, and launch operations. So putting the spacecraft through all the testing that might be that would best simulate the trip to Mars, through the cruise, interplanetary space, entry, descent, and landing, and then the surface of Mars itself. So we call this test as you fly, and then fly as you test, because you want to make sure, however you tested it, you want to make sure that meets the conditions that you expect to have, and then make sure that you still, when you actually do fly, you've done it according to all the tests you've already done. So after we put all of this together in Pasadena, then it was time to get to Florida for launch. Oh, got to mention, who's doing all this? So it certainly takes an incredibly large team. I think we probably had over 2,000 folks over a series of time. This picture is probably at our height of when we had 700 or 800 at Jet Propulsion Lab, but I mentioned that there are certainly folks and vendors all around the country and all around the world. So it definitely takes a huge team to do this. But of course, last year, just like all of us, we had to deal with the pandemic, and we had to really change the way we were doing this. And this was we were supposed to ship the spacecraft to Florida in that January, February timeframe, just when the pandemic was starting to hit. So we had to move very quickly to facilitate that and make sure that we got everything put together and get out to Florida, because if we delayed even just by just a few weeks, we might have been put so far behind that we might have missed our launch window. But once the pandemic hit, about 80% of our workforce, our teams started working from home. And we just had a very small team. Fortunately, most of the building hardware got done, and then there was a small team small team at Jet Propulsion Lab finishing up super clean elements like our drill bits and sample tubes. But then a small team of about 80 or so down in Florida doing the last bits of putting it all together and getting it ready to go on the launch vehicle. And so this is an image of the rover. It's got its wheels tucked up, with protective coverings there removed before flight, but and it's on the underside of the aeroshell. And what I'm pointing out here is it's close to, when we got close to launch, definitely there was, for our team to be able to do what we needed to do, it relied on some folks that kept us all safe, and that's the frontline workers in healthcare and other emergency operations, to make sure that everybody was, as we could do our work safely. So just a few weeks before launch, the team designed this plaque that they put on the rear port side of the rover, symbol of the Earth, with our spacecraft coming up off it, supported by the symbol of the medical community, those frontline workers that really enabled us to do what we do. So we hope that someday when some future explorer might come across our rover and they see this plaque, they'll know what sacrifices that it took, not just from our team, but from many folks around the world to make us safe so we can do what we need to do. So getting this all together, we have what we call the cruise stage, then the back shell, with the rover tucked up underneath, and then the heat shield at the bottom, where we were able to, this is the last bit of all these pieces separated, and the next time they come apart is when they're doing entry, ascent, and landing at Mars. Once we got all that buttoned up, put it in the what we call the launch fairing of the Atlas V launch vehicle, get it rolled out to the launch pad. Here we are, fully assembled, ready to go. Oops. And then launch. Again, beautiful day for a launch. So on our way to Mars, the best time to launch is every 2 years. That's what we call a launch opportunity. That's when Earth and Mars are closest together and able to get there with the least amount of energy. So on the way, these points that are marked called TCMs, trajectory control maneuvers, those are points where we don't have rocket engines on the spacecraft pushing us there. All the energy is given by the launch vehicle, and once we get out of our Earth orbit, we're pushed on our way to Mars and largely coasting. But we do have some small thrusters that we make small changes of the trajectory as we go along. So we did like the first 3 TCMs, but the team was we had such a good trajectory, such good accuracy, that we didn't have to do the last few days. So we really got a great ride. So then on our way to, where are we going to go on Mars, right? Here we have a splayed out map, and we were headed to Jezero Crater. You can see where that is relative to the other landing sites of some of our prior missions. Jezero is really a fascinating place. It's, of course, a crater where we see evidence that used to have an inflow channel and an outflow channel and a long-standing body of water there in the lake, which is now dried out. And the thing that science team really has an interest in is this river delta coming into the crater floor. That's where here on Earth, when you have that type of formation, if you could scoop some of that sediment up, that's exactly the type of place where you would find evidence of microbial life or small life forms. So the team is targeting this river delta. This yellow circle is our landing error ellipse. We knew that we could target somewhere in that area. We were really targeting just right in the center there, right on the edge of the delta. Now, we had a new type of landing technique that had never been done before. Now, the Sky Crane system was the same that Curiosity used, but we added some new technique. This is called terrain relative navigation, where we're able to, as we come down, we're taking pictures of the surface as we're coming down, comparing that with a digital map on board that we already had from our orbital imagery. And then we're able to, if we see that we're coming down towards some hazard areas, be able to do a divert maneuver and get to a safer area. Here's a short video of our landing deck. Plane.
Propulsion, go. EDL phase lead, go.
We have deemed Perseverance ready to execute entry, descent, and landing on her own.
Confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. it will start controlling its path to the landing target. Parachute has deployed and we're seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The back shell has separated. Skycam maneuver has started, about 20 meters off the surface.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
So as you may have noticed in that video that there were some of these images of the actual spacecraft. This is something we'd never been able to do before. A new thing we added was a few commercial off-the-shelf style cameras looking both up at the parachute as it deployed, looking down at the rover. It was coming off the sky crane. And here's one of those images. This is the first image of a spacecraft actually landing on another planet that we've been able or have, you know, from above. So we were just amazed that these worked as well as they did. So where did we land? We didn't land where we targeted necessarily, right next to the river delta. We landed just on the other side of this kind of dune field, what the science team has called a fractured unit. This is their geological map. Different colors mean different things for the geology team. But that's where we landed. Now that fractured unit area is highly covered with sand dunes, so it's not an area that we want to drive through. We want to go around it to get over to the river delta. Now on the right-hand side, you see that red and blue. I mentioned terrain relative navigation earlier, where the red areas are the not safe areas or less safe areas. We wanted to get in the blue areas. So you see, it's definitely a good thing we had terrain relative navigation. We actually were coming, as we came down, we're coming towards a red spot, and terrain TRN was able to divert us and get us down in a safe area. So this is our landing site, right where you see right in front of you there, sort of a lighter patch area. That's where the sky crane thrusters were kind of blowing away as we came down, blew away some of the dust off the rocks. You can see off in the distance the crater wall. And then as we come around here, you start to see there in the distance, almost there, some of the that river delta area as we come along. And then we're starting to see the other side here, again, the lighter patch where the thrusters blew away some of the dust. There we go. Yeah. Now you see the right behind the rover. We landed with our backsides pointed towards the river delta. So a few more images of as we started going, and we're really in our early operations. We've got all our cameras that we can use. I should also mention that SuperCam also has not just a telescope to look at that laser plasma, but a visual camera, and we can really see, really get quite good images of rocks from further away. And what you're probably hearing in the distance is this crunching noise, that low crunch and thump. So in addition to the cameras, we put these a small, actually we have 2 microphones. The first time we've had operational microphones on Mars. One is on SuperCam. It could actually hear the zaps of the laser, and the team actually uses that to help calibrate it. But then there was another just commercial version microphone that we put next to one of those landing cameras. And this is the sound of the rover driving over the surface, and you also hear the whirring noise of there's a fluid loop inside the rover that sends fluid out to the hot radioisotope generator on the back, and then gets heat circulating in through the body of the rover to keep the electronics going. Here's our first selfie. We can use the robotic arm and use that Sherlock camera excuse me, the Watson camera to look back at ourselves and take a mosaic picture. And of course, you'll see that we brought a friend along with us, the Ingenuity helicopter, to the very first time we've done tried to fly on the surface of Mars. Now, this was a technology demonstration and designed to, we really only planned to have it run about 90 days and do as many as maybe five flights. But it has surpassed our expectations and is still working fine. So we transitioned it to what we call an operations demonstration phase. And we're going to be continuing that as long as it can hold out. So another look at our landing site. We landed at the place we named our landing site Octavia Butler Landing Site. And the team had a choice. They could either start going counterclockwise and head straight for the Delta, or go south clockwise and take a little look around, maybe even find a path over to the Delta that way. So we started going straight south. So this is what we call our first science campaign. And we've now driven following this yellow dotted line, and you can see in the red and the blue, that's where Perseverance and Ingenuity are currently sitting. Right now, they're actually taking a holiday. This is a time, as you may be fully aware, of solar conjunction. So Mars is right now behind the sun relative to the Earth, and that's a time we don't want to be sending commands back and forth because one may not even get received properly, or commanding may get garbled. So we have about 3 weeks-ish of where we basically just sort of stand down. So we put the spacecraft, both Perseverance and Ingenuity, into safe, sort of sit and wait it out. Ingenuity is sending signals to Perseverance every couple of days saying, hey, I'm still okay, I'm still okay. And Perseverance is, it's not driving or moving any of its actuators, but it is taking weather measurements, it's taking sound measurements, and taking a few images with its cameras without having to move the actuators. Now, Ingenuity, it started flying. We found an airfield near our landing site, and that's where we did our most of our test flights. And then as we started driving south, we would do hops so that Ingenuity could follow Perseverance along. And one of the neat flights was this flight number 9, where we, instead of following Perseverance, we went straight across that fractured unit where Perseverance cannot drive. And that was its longest flight, and we were able to meet on the other side. Up until, we've done about 13 flights now, and the last 2 were really the first ones that were really designed to do some reconnaissance for the rover itself. So far, it's really been technology type operations demonstrations, but now we're actually using it as a tool to help the science team decide where to send the rover, which is a tool we have not had before. So here's an image from the helicopter in the air, crossing the Seta. And I mentioned we're on this first science campaign. So this is the broad general type of landscape. You see these paver stones and a few other bouldery rocks along the way. And these what the team is calling paver stones. These are one of the first ones that we tried to sample. Now, doing that can get challenging. This is a close-up view using the Watson imager. trying to determine what this rock is really made of is challenging if you have all this dust and little granules on it. So what we like to do is use our robotic arm, both to take using our cameras and the Pixel and Sherlock to get a sense of what the rock is like in its natural state. And then we can start doing, oh, I'm not at the abrasion yet. This is the first, what we call the campsite. This is the area where we said, all right, we're going to really start doing some interrogation on a set of rocks. Most of the drive down south, we were just using our cameras, remote sensing science. Now we wanted to get down and really look at the rock in detail. So the first thing we want to do is use another bit that we have. We call this the abrasion bit. So it has these very sharp teeth on it where we can abrade away the rock and get rid of that rough surface texture and get a quasi-smooth point for Sherlock and Pixel to be able to really look and see what the makeup of the rocks are. Oh, there's an image of our abrasion bit. Close up with that patch. So we took our very first sample of one of these paver stones, and the way we designed our sampling system is in order to do sampling very efficiently, you want to be able to do it as autonomously as you can. You don't want to have ground in the loop as much as you can. So what we did was sent the command, go do the sampling, report back. So it did, and lo and behold, on the bottom right is actually an image of, I mentioned there's a camera inside the rover that can look down in the tube. That's looking down the tube, and it's completely empty. So this was a bit of a mystery. And we looked like, well, what happened to the core? Everything worked perfectly. The whole system worked as planned, but there's nothing in the tube. So we looked down, this is the borehole, and we couldn't even find much of a, we thought, well, maybe it just fell out, right? But we don't really see much of like a core in there. But you'll notice the tailings are really quite large. And so what we think happened was that this rock was a lot more fragile than we expected. And so as it was, as the drill bit was drilling into it, what would have been becoming a core was just being spun out through the flutes on the side, or some just fell out at the bottom of the borehole. So we had, one of the things we can do with SuperCam is after we drill a hole, we can fire the laser at the hole down into the layers to actually get some data on the rock itself, not just on the surface, but down in it. So these little holes are what happens when the laser hits it. Another picture from helicopter flight. You can actually see in the bottom there, you see the shadow of the helicopter. So we found a rock that we felt was a little bit more, wouldn't come apart as much, that we named Rochette, and did our very first drilling. And this time, everything worked as planned. But just to be sure, we added one ground in the loop. But before we brought the tube inside the rover to look at it, we looked at it with the cameras on the end at the top of the mast to make sure there was really something in there. Yes, indeed, there was. So we were able to send the command to then bring the sample inside the rover, process it, seal it, and put it in the storage area. And there's this image of the tube, looking down on the tube inside the rover. Another image from after that sampling of Ingenuity going off to look, study the path, the notional path that we had for the rover coming up. So that's where we are. We are, let me go back to that. Let me do it. This area, South Seta, is where the rover and Ingenuity are currently sitting now. Perseverance itself is more along some of the rockier areas, but that's where they're sitting out Solar Conjunction. So at the beginning, when I showed the video, you saw briefly the image of the parachute. And it has this interesting design on it. Many parachutes have stuff like this, so that if you're uh, as the parachute is inflating, you can, if you're doing a test on it, you can use those markings to help study how well it's inflating and do some metrics on it. But when I saw this, that was quite an unusual design, and I had not seen this design before the launch. And I immediately thought, I think my JPL team has done another, hidden another message. They did that with Curiosity with its wheels. They put some holes in it that are in Morse code, such that as it drives on the surface of Mars, it spells out JPL, JPL, JPL. And we didn't necessarily know that's what was on the wheels till we got to Mars. This same thing, I was not aware that we had this design, and hidden in it is also a message. Using binary code, it spells out "Dare Mighty Things," which is the motto of JPL, as well as the latitude, longitude of the center in Pasadena. So I got to hand it to my team. They snuck this one by me. There's several other what we call embellishments on the rover, whether it be plaques or markings that we approved. But this one was a surprise, but it was definitely a welcome one. This team definitely did their mighty things. So I certainly hope that you will keep following along with our mission, and you can follow us on social media. You can also go to our website, mars.nasa.gov, and /Mars 2020. Follow everything that Perseverance and Ingenuity are doing, because there's we definitely have an exciting mission ahead. We've only been on the surface a few months. We have a prime mission of 2 Earth years, a little over 2 Earth years, where we're going to be trying to do that collecting. So once we finish out of solar conjunction, we're going to start driving back along the track that we came from, back towards the landing site, and then go north counterclockwise and head towards that river delta, which is one of the places we really hope we might find some of these ancient microbial biosignatures. So with that, I'll take any questions and answer from there.
Thank you very much, George. I think Laura was collating the questions. I saw quite a few coming in while the talk was going on. So Laura, are you ready to ask, or do you want to do your draw first?
I think we'll do the questions first, Dave, and
Yes.
then we'll do the draw. But we have got a winner for the draw.
Oh, keep everybody in suspense. Okay. Well, in that case, do you want to read out the first question?
Yeah, Sharon Donahue asks, can you tell us about the current alive status and expected longevity of the rovers currently on Mars?
Sorry, the what status?
Alive status?
Oh, of the various spacecraft we have. I think if I understand that right. Yeah. So
Yeah.
of course we have Perseverance and Ingenuity, our brand newest. The other we have 2 other NASA assets on the surface. One, of course, is a Curiosity rover at Gale Crater, still going strong. It's climbing Mount Sharp, which was its destination. And then we also have a static lander called InSight, which is, even though that's not part of what we call the Mars Exploration Program, it's part of a different planetary program we call Discovery. But it's has a seismic station on it, so it's studying Marsquakes and has detected several of them. And it's studying the interior core of the planet. And that we have several orbiters, Mars Reconnaissance Orbiter. We have another orbiter called MAVEN and Mars Odyssey. So those are the US NASA systems. Now, the other thing that's on the surface of Mars, we have a new player in the game, and that, of course, is China with their Zhurong rover that they landed shortly after we did.
Perfect. Our second question is from Sam O'Riordan, and he wants to know, is there still a helicopter on Mars?
Yes, there is. Ingenuity is healthy, doing extremely well.
John Campbell asks, does the Ingenuity helicopter incorporate any autonomous feature of interest detection systems that work in tandem with the rover for remote sensing and or mapping applications?
So Ingenuity is incredibly autonomous. We, of course, because of the light time delay, well, everything with the rover, there's no way that humans can joystick control anything. So everything has to be, all the commands sent ahead of time, and Ingenuity has to be able to have sensors to be able to tell how high it is, how fast it's going, what the terrain is looking like underneath it, to a certain degree, and do that all autonomously. Now, in terms of, it does have two cameras. I mentioned one download camera, again, to basically see the terrain for navigation, but then it has one other camera, which is, that's the color camera, the images I was showing, mostly just for fun. Well, not for fun, but, just to see, can you do that? And it works fabulous. So now we are able to use it in an operational sense, so that the science team can look at those images and help combine those with images we already have from orbit, and help get a sense of where they might want to send the rover to do some of its own science. So that's how they're working together now.
Okay. Selena writes, her son Liam, who's 9-year-old and is fascinated watching, wants to know what would be the approximate weight of all the samples that will come back to Earth.
The approximate weight of all the samples. I am glad you asked that. I don't think I've ever been asked that question before, and I do not know. I'm going to have to write that down and get an answer just so I'm ready to go.
Clodagh asks, has the weather on Mars impacted on the rover?
So the weather on Mars, it's very harsh, extremely cold. Again, I mentioned the radiation environment, but you do have a lot of fluctuations in temperature. Now it's still all very cold, but for a robotic system, particularly made out of metal, lots of stresses and strains on the system. So it does on a daily basis. The temperature range does fluctuate quite a bit. So it has to be designed to endure that. And of course, we have the dust environment. Can be, even though the atmosphere is not very thick in terms of if you have dust blowing, so it's not too harsh or abrasive, but the whole spacecraft does have to be able to endure that, getting any kind of dust on the surface. So, and that's pretty much what you have for weather. There's certainly no rain or precipitation or anything like that, given that the atmosphere is simply so dry. And yeah.
Okay. Tom Finnegan asks, is there a possibility of regolith degradation if it is left for a long time after sampling without being collected?
Is there, what's the word, something degradation?
Regolith?
Oh, no. If I understand the question correctly, does the regolith degrade the rover?
Sorry, George. I'll just ask Tom to unmute and ask the question himself, if he doesn't mind.
Yeah.
Hi, George. George, I was just wondering if the samples that are taking and now, if they're not going to be collected for a couple of years, maybe when ESA sends a craft to to Mars, is there a danger that they may have changed in composition in some way, or just broken down somehow?
Right. That is actually one of the considerations as we were designing mostly these tubes, right? Because that's where the sample is going to be. And we wanted them to be able to maintain the integrity of the sample, over 10 years or more, right? before the retrieval missions come. That actually has something to do with the coloring. This isn't exactly but it has this white coating to help keep the temperature down, keep it from not getting all that hot. But short answer is no, we do not expect any kind of degradation of the samples sitting inside the tube. They are hermetically sealed, so we don't expect anything to be able to impact them whatsoever, sitting on the surface waiting for that long period.
Okay, that's great. Great answer.
Christina asks, assuming it's fully charged, how long would Ingenuity's maximum flight time be?
Maximum flight time.
Yeah, maximum.
That's a good
flight
question.
time.
I don't know the maximum, but it can be. I'm going to have to look that one up too. I don't know a maximum. It's not that long. A matter of minutes.
Yeah, it's a big mission, so we can't expect George to know absolutely everything. But one thing I would say is any of the questions that you want to look up the answers to, George, Anne, our managing editor of the magazine, will be doing a report on the lecture. So if you do find out any of the answers, we could actually append them in there and just email them to editor@astronomy.ie. Indeed, anyone listening can email any questions they want. If we know the answer, we'll tell them. But if you have the time, George, we'd appreciate that.
Sure.
Edward Malarkey says, congratulations to you and your team. Great work. First of all, has it taken any photographs of Earth?
Have we taken any photographs of Earth? I don't think we have yet. I know Curiosity has, and it would appear like a star in the sky. I don't think Perseverance has done that.
Okay. And secondly, he asks, can you speak briefly about possible energy sources on Mars?
So this comes back to our preparing for future human exploration, right? When we send human crews, we definitely would want to be able to use as many resources on the planet as possible and not bring them along. And energy would be a key one, right? Now, we have no evidence of, if you talk about energy resources like we have here on Earth, like oil or those sorts of things. Yeah, we wouldn't. That would be great if there was oil, because that would mean there had been tremendous amount of, organic life form of some sort in an ancient past, perhaps. But we definitely have no evidence of anything like that. So your main energy source is solar power, like you have on any planet you'd have available. But another key resource that we would want to be looking for is water ice. In addition to using the atmosphere to generate oxygen, if you have water ice, of course you need water for survival, and then of course you can break that apart to get hydrogen and oxygen. And the hydrogen now can be used as you can burn that as an energy source.
Okay. Nick Dunn asks, since most cameras have an operational temperature range of 0 to 40 degrees Celsius, how are the cameras on Mars still functional with extreme temperatures?
Can you say that one more time for me?
Yeah. So Nick asks, since most cameras have an operational temperature range of 0 to 40 degrees Celsius, how are the cameras on Mars still functional with extreme temperatures?
Yeah, because our temperatures are way below that. So definitely these are not your typical off-the-shelf cameras. Aside from the ones that we use for the descent imaging system, they're specially designed for this type of environment and put through all the environmental testing that we can do here on Earth to make sure they'll last for many years on the surface of Mars.
Okay, great. Patrick asks, what is your favorite part of the mission?
Oh, that's a good question. It's got to be the sample tracking system. I mean, this thing is the most complex thing that we have ever built and sent in a spacecraft. It's incredibly precise. And another key thing, one of the biggest challenges we have with the sampling system is to get it ultra clean. Because when we have these samples, we don't want to be not only the mechanisms, but the rest of the rover. I mentioned planetary protection earlier in the talk. All spacecraft we send to Mars, going to Mars, we want to clean them to a certain level so that we have confidence that down to a certain what we call bioburden level. We don't want to bring Earth contamination to Mars that might, as we're going around trying to look for Martian life, we don't want to find Earth life that we brought along with us, right? So we have that level of planetary protection, but since that's a standard that we've had for many spacecraft, but for these samples, because we're potentially going to be doing life detection type experiments on the samples when we get them home, we want to make anything that is what we call sample intimate hardware. So that's the tube or these drill bits or the plugs that go in the ends. We may want to make sure those are even ultra clean, cleaner than any spacecraft we've ever sent to Mars before. In fact, we had requirements for less than one. What do we say? We had a certain amount of. We had both microbial requirements as well as limits on what we call total organic carbon. Just, sitting out in the air, there's carbon in the air that can precipitate on a monolayer if you're sitting in the spacecraft assembly facility. So we had to come up with techniques that could clean as much of that off as we possibly could, and get these things such that when they come home and we're trying to study them for potential signs of life, we're confident that it is actually Martian and not terrestrial. Now, the other thing we have with these tubes to also help in that investigation is what we call witness tubes. So we get 5 of the tubes are not empty when we took them along. They have inside them material that is, we call a getter. It's a collector of any type of terrestrial contamination, particularly organic contamination that we might get in there. So we use these witness tubes and we put them through the entire process, same process, even putting them in a drill bit and putting them out on the end of the arm. We don't put them next to a rock, but then we bring it inside. And that way it has gone through the same process as all the other tubes, but it can give us a sense of, is there any kind of terrestrial contamination coming off the rover that might get in the tube? So when we bring home the samples, we'll be bringing home a couple of these witness tubes as well.
Just to add to that, George, could you be sure that there wasn't one single microbe in one of the sample tubes?
Well, like I say, we had these cleaning protocols that are way beyond what we've ever done before, and the requirement is less than one viable organism. So that's incredibly stringent.
Yeah. Wow.
George, Christina asks, what is the plan for the samples once they return to Earth?
Good question. So they'll land in the Utah desert, and then we'll drive out there with a specially designed van or a vehicle, want to say, bring the whole landing container inside that, and then that would be driven to what we call a special receiving facility. That would be the type of place that can do 2 things. One, protect the samples from, again, terrestrial contamination, but also another piece of planetary protection is called backward protection. There's forward that I already talked about. There's backward, which is any place where in the solar, basically from Mars, but there's a few other places that we call have certain we'll call restricted Earth return requirements for coming back to Earth. Even though there may not be any evidence or expectation that there is any kind of harmful thing inside these tubes to the Earth environment, we're going to treat them as if they are hazardous, just in case. as a precaution until they're proven otherwise, right? So part of what this receiving facility, that dual contamination protection, is for keeping Earth contamination out and also making sure that any Martian material stays in until such time we can do the diagnostic tests on them, make sure they're safe, and then we can cut up the small samples and distribute them to either do analysis on them in that facility or distribute them to other research facilities around the world, not unlike what we currently do with other what we call astromaterials. Largely, a lot of the samples we brought back from the moon, but we've also brought samples back from other. On its way is like our OSIRIS-REx mission, bringing back some asteroid samples.
I see we have about 3 more questions, Laura, if I'm correct. We don't want to keep George all night or all day in his case. He's 5 hours behind us. But I wonder, George, would you care to speculate on when the mission is all said and done? I know it'll only be a guess. What do you think is, say, the percentage chance that you will find evidence that there at least was life on Mars? Your best guess.
There's no way to speculate, quite honestly. I certainly hope we do. If Jezero Crater, again, the science community, actually the picking of the landing site was a multi-year effort to try to find the best site that might have the right type of landform and rocks to preserve potential biosignatures. And all across Mars, this is definitely one of the best types of environments to do that. It's the right age, around that, a couple of billion years old, and having that inflow channel and the river delta, that's exactly the type of place you want to look. So I think, we have the best chance that we probably will have. Percentage-wise, no way to tell, but certainly have high hopes.
Okay, you don't mind taking, say, I think there's 3 more quick questions?
Yeah.
Over to Laura.
Sorry about that. Jessica asks, what happened to the parachute after Perseverance landed?
So as we're coming down in pre-descent landing, the parachute and what's called the back shell that it's attached to detaches from the sky crane and the rover. So this is the rover, the sky crane is on top of it. They detach from that whole system. And as they're coming down, I mentioned the terrain relative navigation divert maneuver. We also have to do a divert maneuver anyway to make sure we get away from that parachute. We don't want the parachute and back shell to land on top of us. So the divert maneuver was also not only to be able to find a safer spot, it had extra fuel at. It was to get away from the parachute back shell, and then we could use some extra bit of fuel if we needed to get away from an unsafe spot. So the parachute is laying on the surface of Mars. You can actually, some of the images you can find on our website, we've been able to see where that landed using the Mars Reconnaissance Orbiter, and it's very close to the landing site.
Brilliant. And Sarah asks, have any terrestrial samples been brought to Mars to test for reactions in the Martian environment?
Can you read that one more time?
Have any terrestrial samples been brought to Mars to test for reactions in the environment?
I wouldn't say it that way. If you mean like, have we brought any plants or anything like that? No, but actually, something we do have on as part of the Sherlock investigation, and this goes back to preparing for human exploration. The Sherlock and Pixel both have what we call, and SuperGAN have what's called calibration targets, small targets with different chips of different material or to be able to look at, because the instruments will want to say, okay, I'll do a measurement on a known thing from Earth so that I can calibrate that based on what I'm seeing on the rocks here on Mars. And the Sherlock calibration target actually has some materials that types of fabric or harder materials that you would use in manufacturing spacesuits for future space explorers. So we're actually, as the mission goes on, we're going to be looking at those to see how they might degrade in the environment, and that will help inform design of future systems for humans.
Okay. And just lastly, Jessica asks, her sister wants to know, what would you do if you find a living thing on Mars?
Oh, jump up and down and enjoy. That's yeah. So now again, we don't expect to find anything currently living on the surface of Mars. The environment is really just too harsh. That is why we are looking into the ancient past. Now, and we've landed in a place where the rocks, we believe, are that old based on relative age dating from crater counting and the best estimates of the science community. But if you wanted to look for existing life, you'd probably have to look under the surface a little bit. And there's actually a mission that's going to attempt to do that. And that's the next mission that'll launch in 2022. And that's the ExoMars rover, Rosalind Franklin, that ESA is sending jointly with Russia on a Russian lander. So it has a drill that can go a couple of meters below the surface and bring up samples, powderized samples. And then there's some instrumentation inside that rover that can look and see if it can see any potential signs of life. So that could be potentially exciting. That might be our best chance to find anything that's, extinct.
And just finally, Edward Malarkey said, to reach your high position in NASA, what is your own background? Was it engineering or astronomy?
So I'm a little bit, my path to my current position, a lot of folks in NASA, they certainly start out in their undergraduate university level doing some sort of hard science, engineering, like to say astronomy, something like that. And then sometimes they usually go to graduate school and expand on those capabilities, or maybe they go a little bit different route. They might learn about science, technology, policy, or business, or something else to round them out. I kind of did it the other way around. I started in my university level was political science and computer science, and that's how I got started. Then I did graduate work in science, technology, policy, and then I went back for another degree in systems engineering to get some more technical credentials. So while I may have all of it together, I kind of did it somewhat backwards compared to maybe most folks in the NASA community.
Fantastic. Great career path there for anybody listening in. I think that's the end of the questions, because we'll have to let George go. He's been fantastic this evening. Do you want to stay on for the draw, George, or do you have important work at NASA to get back to?
I do have some meetings coming up, so it'd be good if I can break off and get prepared.
That is fantastic. Let me thank you from the bottom of my heart. I'm sure from everybody listening in, that's one of the most phenomenal sets of questions I've heard. We're going to be following the Perseverance mission through the pages of our magazine, hopefully for many years to come, and all the future exploration. And to get somebody from near the top of that pyramid of people that you showed, which for me was one of the most stunning images, just how many people were involved with that mission staggered me. It really brought it home, that one picture. So thank you, to your entire team, and we wish you every success and luck in the future. And thank you so much for helping us with World Space Week.
My pleasure. Thank you for having me. Cheers all.
Thank you, George, and goodbye. And I'll hand it over to Laura to do the draw.
Okay, so we have everybody's name on a list, and we've done a random number generator. And our first prize of the binoculars goes to Andrea Coyle in Wicklow. So well done, Andrea. We'll get those posted out to you. And our second prize of the family pass to Blackrock Castle Observatory goes to Derek Parr in Malahide in County Dublin. And we'll get that posted out to you as well, Derek.
Thank you.
No problem at all, Derek. Enjoy.
And congratulations to the winners there. That's everything, Sonia and Laura, isn't it? Any other announcements I need to make, or will I just close the meeting?
Just about our evening classes starting on Tuesday. If Tuesday doesn't suit, get in contact with us. We can help you out if it's another day that is more accessible for you.
Great. Yep, I know there'll be lots of bookings coming for that. It's extremely popular, especially last year during all the lockdowns. I think we broke all of the records. Thousands of people have taken those classes. Now is the next big thing in Astronomy Ireland next Tuesday. But don't leave it till then. Try and enroll this week. Right. Well, I think that's the formalities over. I'll just tell you briefly about the next talk, which is in November. I think that's during National Science Week. If I'm not correctly, it's November the 8th, and it links in nicely to this particular talk in that it's all about space, microbes in space. So, you know, the human body, I believe, has 10 times more bugs in it than we do of our own cells. So they're going to follow us into space, and Rosa Santa Marino is going to give a talk. She's currently based at Edinburgh University, but she's worked for NASA as well. She's flown missions on the International Space Station linked to this kind of talk. So if you want to know more about bugs in space, how they're going to help us, how important they are, how dangerous they are, then go along to astronomy.ie, book your tickets for the November 8th talk, and we'll see you all there. We might see you as well on October 30th at the Starbecue. We're planning for it to go ahead. Only the government can stop us. And I don't think that's going to happen. The figure's looking very good. So if we don't see you at the evening classes next Tuesday, we'll hopefully see you on Saturday, October 30th, the day before Halloween, the night that the clocks go back, for the biggest annual star party in Ireland, Starbecue, a barbecue under the stars. With some of the most powerful telescopes showing you the wonders of the universe from a really dark sky in the Wicklow Mountains. And then we'll see you on November the